This is my circuit designed to get the sound output such as heartbeats from the stethoscope. This can be called a biomedical signal processing system. It allows the end user to listen to the heartbeats through the circuit. I will explain the circuit and its functions. There are 4 stages to this circuit, each serving a specific function. Let's go through each stage step by step. For the stage 1, we will start with the preamplifier using the TL072S ICA1, which is a dual low noise JFET input general purpose operational amplifier. This preamplifier boosts the signal from the transducer to a level suitable for further amplification. In an audio amplifier system, a microphone acts as a transducer by converting sound wave into an electrical signal. A preamplifier boosts this electrical signal from the transducer to a line level so it can be further amplified to drive the loudspeaker, producing the final output sound. It amplifies typically a voltage gain between 10 mV to 1 V, but does not provide current. The op-amp amplifies the audio signal, adding or reducing subtle shades in the sound character. Based on the circuit, it is a fixed-gain closed-loop non-inverting amplifier. Capacitor C1 blocks the DC bias voltage from the input but allows AC voltage to pass through. The voltage divider consists of two 10 kilo ohm resistors, R5 and R6, setting the op-amp to operate at half the supply voltage, 4.5 volt, in single supply mode. The resistors R2 and R3 and capacitor C2, C3 form the bandpass filter. The bandpass gain is calculated as 23 using the formula ACL is equal to 1 plus RF divided by R1. Here we use R2 as RF, and then we get the value of 23. The coupling capacitor C4 connects the output from the first amplifier stage to stage 2, blocking DC offset but allowing AC signal to prevent DC offset amplification, which could reduce headroom and cause clipping. Stage 1 operates in single supply mode, so a level shifter, which is a voltage divider, is added to move the waveform outwards, preventing any parts from being cut. From this table, as the frequency increases, the gain also increases until it reaches a maximum of 23 at 100 Hz, which is 27 dB. After 23, the gain drops gradually. Frequency higher than 100 Hz will cause the gain to drop. And then from this frequency response curve, the AV line is drawn at 24 dB, and then the bandwidth is calculated by using the formula higher frequency minus lower frequency, and then we will get the value of the bandwidth. For the setup for stage 1, the power supply is set to 9 V, channel 1 connected to the negative capacitor C1, and channel 2 to IC1A pin 1. The function generator is set to 1 kHz and 200 mVpp. From the stage 1, we can calculate the voltage gain by using the formula V out divided by V in. And we can see the sine wave of channel 1 and channel 2. And the frequency both channels display 1 kHz. Stage 1 amplifies the input signal from the transducer, making it strong enough for further processing, effectively capturing heartbeats clearly. For the stage 2, the same IC is used for another stage as a negative feedback loop amplifier. This is how the output voltage of an amplifier is returned to the input with 180-degree out of phase. This stage focuses on adjusting the gain and ensuring the output signal is properly centered to avoid clipping. Negative feedback stabilizes the gain and improves the linearity of the amplification. The output voltage is returned to the input 180-degree out of phase. The trimmer adjusts the feedback signal, decreasing the overall gain and ensuring linear amplification, preventing saturation. A voltage divider made out of resistor R9 and R10 enables single supply mode and functions as a level shifter, preventing output clipping. C5 also acts like C1, blocking DC voltage and coupling the AC. For the stage 2, we can see how turning the trimmer can affect the output waveform. And as I adjust the trimmer, the waveform will be amplified and at some point, it becomes saturated and be cut off. So, clipping indicates excessive gain. Proper trimmer adjustment avoids distortion, ensuring accurate heartbeat signals. For the stage 3, capacitor C5 blocks DC, allowing AC signals through. A voltage divider R11 and R12 provide single supply mode for the second TL072 and function as a level shifter to make sure that there is no clip waveform. The second IC2A function as a Sallen-King second-order low-pass filter consisting of two low-pass RC networks. Capacitor C7 shape the response near the bandpass edge, allowing low frequency and blocking high frequency. Capacitor C8 smooths the signal and block DC. Using the lowest frequency, which is 0 Hz, we can find the cutoff frequency. The filter maintains unity gain below 500 Hz. As the frequency exceeds 500 Hz, both gain and output voltage decrease. From this graph, the -3 decibel line indicates a bandwidth of 1 kHz, which is similar to the cutoff frequency. For the stage 3, channel 1 is connected to IC1 pin 7 and channel 2 to IC2 pin 1. As I turn the trimmer, both channels become flat. Trimmer P1 controls the gain or offset voltage, ensuring a clear and precise heartbeat signal for further processing. Adjusting TP3 affects the output waveform at TP4. At 100 Hz, waveform amplified at unity gain. For IC3, we use the IC-LM386N1, an audio amplifier in single supply mode, providing current to power the speaker. Capacitor C15 eliminates high frequency above 40 kHz, ensuring output stability. Capacitor C13 prevents DC while allowing AC signals. The input signal goes through the trimmer P2. Channel 1 is connected to IC2 pin 1 and the negative side of capacitor C13 is connected to channel 2. Adjusting trimmer P2 controls the output at TP5. Turning the trimmer can remove unwanted components. Adjust trimmer P1 to troubleshoot any sine wave distortion, ensuring a clear heartbeat signal for the end user. This completes the explanation of our biomedical signal processing system for amplifying heartbeat sound. Thank you for your attention.